sun is exploding with flares, bright arcs of plasma ripping out into space, each one powerful enough to swallow worlds. But out there, cutting smoothly across the darkness, 3i Atlas doesn't even flinch. No sudden shift, no wobble, no deviation from its predicted path. It looks impossible at first. How can something so small ignore storms that shake the whole solar system? The answer begins with a simple measurement that astronomers swear by: residuals. Residuals are tiny gaps, fractions of an arcsecond, between where the math says 3i Atlas should be and where telescopes actually see it. If a real force were pushing it, those gaps wouldn't stay random. They'd start leaning in one direction, night after night, slowly drifting away from the prediction. That drift is the signature of something real happening. But right now, the opposite is happening. Even with the sun roaring in full display, the measured points of 3i Atlas fall almost perfectly along the prediction line. The orbit isn't swelling, twisting, or spreading out. The track stays tight, calm, predictable. Think of it visually. On one side, you have the sun throwing out flares and violent coronal mass ejections. Huge clouds of plasma racing outward at millions of kilometers per hour. Then you look at the orbit chart and everything is quiet. No reaction, no shift. Just the same clean path carved through the sky. Why? Because solar storms look powerful, but their force spreads out across a massive area. By the time that energy reaches a tiny interstellar visitor, the push is unbelievably small. Here's the easiest way to picture it. The pressure of sunlight hitting a 1-meter object at Earth's distance is like the weight of a few paper clips. Meanwhile, the sun's gravity pulling on that same object is like a truck towing it on a long steel cable. A flare or mass ejection might brighten the sky, but compared to gravity, its push is nothing more than a whisper. To truly move something like 3i Atlas, you need a force that doesn't just spike. You need one that lasts, one that builds, one that pushes in the same direction day after day. Only one thing can do that: outgassing. Tiny jets of vapor escaping from inside an object when sunlight warms hidden ice, like miniature thrusters firing over and over again. That's what moved comets like Isun before it broke apart. That's what nudged 2i Borisov. That's why Oumuamua became such a mystery, because it showed a small push with no visible coma. Outgassing leaves fingerprints, a light curve that brightens in step with sunlight, gas lines in the spectrum, a coma that drifts off-center, and most importantly, a steady, growing lean in the orbit. But for 3i Atlas, those signatures aren't showing up. The brightness changes match simple heating with no explosive spikes. Telescopes see no obvious coma or tail forming, and the orbit still fits perfectly with gravity alone. If 3i Atlas had jets firing, those residuals would already be tilting in one direction, but they're not. Orbit analysts follow a strict process. They start with a gravity-only model. They watch the residuals over days. If the gaps begin lining up consistently, they test non-gravitational terms, A1, A2, A3, parameters that describe tiny thrusts in different directions. But they only keep those extra terms if they make the entire data set cleaner across multiple nights. If the fit doesn't improve, they reset back to the simple model. For now, that simple model works perfectly. The uncertainty envelope, the cone that predicts where 3i Atlas should be days or weeks from now, is stable. It isn't expanding faster than expected. It isn't stretching or drifting. It's behaving exactly the way a gravity-ruled path should behave. And that stability is a gift. It means astronomers can schedule deep imaging runs with confidence. It means spectroscopic studies can focus on subtle details. It means long-time series photometry can capture tiny changes without the risk of losing the object. The calm orbit buys us time and clarity. When the sun erupts but the object does not respond, it tells us one thing. Solar drama does not equal orbital drama. Space weather looks wild, but physics is still king. 3i Atlas is not being shoved. It's not drifting. It's not hiding any mysterious force. At least not yet. If that changes, the first sign won't be a flare. It won't be a headline. It'll be a whisper in the data, those tiny offsets between prediction and reality starting to lean night after night. So for now, the message is simple. Watch the residuals, not the eruptions. Follow the next updates from MPC, JPL, and observatories posting fresh astrometry. If the orbit shifts, you'll see it traced in numbers first, and we'll cover it the moment it happens.